Okay, so if we can do the law of reflection on curved surfaces, it means we can also do the law of refraction on curved surfaces. So let's say that I have some kind of refracting surface, and this has some index of refraction. We'll just call it n and say it's greater than 1. And we'll just say that out here, this is n equals 1. So if we have a light ray come in, it'll strike that surface, bend a little bit toward the normal line of that surface, right? So it kind of gets bent here. And then across this normal line, it'll kind of bend a little bit away. It might do something like that. And as we have more of these things do it from different angles, right? There's bending inside, there's bending back out. They do the same thing that the mirrors did, and we have some kind of a focal point on the other side. There's an equation to deal with this. It's called the lens maker equation, and it kind of deals with the difference in the refracting indices and the fact that this happens on two sides, and the different radii kind of change how it focuses. That's all on spherical refracting surfaces, and you can look that up kind of on your own. It doesn't matter right now. So when we look at these, how do we deal with thin, with big quotation marks, lenses and surfaces? We've got two equations that are important. Well, that one looks pretty familiar, and this one. And in fact, this is called the thin lens equation, but it applies to mirrors also. So both of these that you've dealt with, either concave and convex mirrors or lenses, they work with the same equations. Everything about them is the same, except for one key difference. So when we looked at the mirror, and we'll label this as mirror so we know, if we have our object over here, the light comes in, it strikes the mirror, and you expect it to reflect off. So anywhere the light goes is the positive side in this situation. And back here behind the mirror, that's nonsense, right? So that's a negative. When you deal with lenses, if this is our object and the light comes in, what happens when it strikes the lens? It should go through it, right? So the light should transmit through a transparent medium. So that makes anything on this side positive, and anything on this side will end up being negative. So that's all you really need to do to keep lenses and mirrors separate. They use the same equations, but when we deal with, is this concave or convex? Is it converging, diverging? How do we deal with the signs? That's when you want to look at this situation, right? Follow the light. Does it go through or does it bounce off? And that will be the key in helping you figure out what is a sign convention for this particular device that you're working with. Yeah, so why don't we just dive in and do some ray diagrams. How about we set our 0 point to be here, and we'll do 1, 2, 3. Okay, and how about we set our focal point to be 10 centimeters. That is the middle, right? Yeah, that's the middle. So a question we need to figure out, how do we deal with the focal point? Is this positive or is it negative? A trick that I use for the convex lens or the converging lens, any converging lens can be made with a lot of different orientations, and we'll try that out when we get to making glasses. But typically, the converging lens is also represented as double convex. So use kind of the same stuff that we did with the mirrors. Let's see, maybe a different color would help. Focus your attention on this first surface and ask yourself, if this was a mirror, how would you go about finding the focal point? Well, we'd say the focal point is half the radius from the first surface, or if this was a mirror, the mirror's surface, the center of curvature would be over here. So that means the focal point would also be on this side. So if that's the case, this is assuming my object is over here, which I guess is now 15. If that's the defining positive side on this side, then the focal point is positive based on this first surface. So we'll call that F. Okay, so when we do the when we do the rays in the ray diagram, there are three options that we have to choose from. The first one is come in flat, just like we did before. So let's make this, I'll write it down here. Come in flat, and then transmit through the focal point. So we'll come in, we'll go all the way to the plane of this lens, and we want to make sure we go through the focus. And I guess I'll be a little bit careful here, just to make sure that we get that. Okay. The second one will be aim for the focal point and then come out. No. Go for the center. Go for the middle. And then just keep going. And this is in some ways the same as the bounce back at the same angle, except at this point you'll transmit at the same angle. All right, so we get something that looks like this. Oh no, and my image is gonna be way off the frame. So the image is somewhere over there off the page. There is another option, and it's one I don't really like. Because there are two surfaces, I guess we could consider that there might be a focal point over here. And I call this the fake focus. Why? Because it's only good for a ray diagram, for only one of the three rays in the ray diagram, and it's not a true focal point. All of the geometries and refraction and all the equations, everything gives us this as the true focal point. Okay, but there's just another one that can be useful in the ray diagram. So if you want to use it, and it's dangerous, aim for the fake focus and then come out flat. And that'll make for kind of a bad picture, right? Because it's just off the pane. We'll come here to the plane, and then this focal, or this ray would go again off the page. So we can kind of come up with maybe an idea of where the image is. Let's kind of pretend extend this. These rays would go somewhere about here, it looks like. So my image is, let's see, probably about there. What can we say about it? It's inverted. We can say it's got an image distance of 1, 2, about 30. Right, and that's a rough guess, and this is 5 tall, so I think my magnification is about -2, and it's minus because it's upside down. And the last question, is this real or is it virtual? Well, real for the mirror meant on the same side as the object, but for the lens, it means on the opposite side, because that's where the light really goes. I can't put a piece of paper up here and expect to catch the image, because then I'll block the light and it'll never make it to the lens, right? So this side is the real side due to this positive sign. We think this image is real. So let's check our work according to the equations that we had. Hopefully my arithmetic skills can get us through this. So we want to do 1 over F is 1 over P plus 1 over I. Our goal is to solve for I, so 1 over the focus is 10, is 1 over the object is 15, plus 1 over I. And these can be converted into units of, or denominators of 30, I think. So multiply top and bottom by 3, Got 3 over 30 equals, to get 30 here, I need 2. So 3 minus 2 is 130. Equals 1 over I. Well, that seems to imply that I is plus 30 centimeters. That actually was a really good guess. I didn't try that out, and this was completely done cold, so that's a decent guess on that picture that we drew off the page. Okay, this automatically tells us it's real because of that sign. And then, to find the magnification, of course, it's negative I over P, which is minus 30 centimeters over the 15 that we started with, minus 2. And it's inverted because of that sign. So that's how to do a ray diagram. Come in flat through the focus, just like the mirror. Go for the center and same angle, just keep on going. And if you really want to try the third one, you aim for the fake focus and then come out flat. It's pretty much step 1, just reversed. All right, so what other angle or what other types do we have? We saw that this one converged the rays, and just like a concave mirror, the convex lens will do the same thing. So we'll redraw the picture. Okay, last time we had a focal point of 10 centimeters, so why don't we keep that? And I had an object that was at 15, right? I guess this is fake F2. My object was at 15, which was outside the focal range, which I know we said the focus was on this side, but this range extends to over here for the lenses also. So why don't we instead bring it inside? So that'll be the object, and we'll put it at 5 centimeters. Before we do any of the calculations, let's do the predictions. So we want to come in flat and then transmit, refract, whatever we want to call it, through the focal point. And I've got some intuition about this one because we've done this with the mirror. There's a good chance this is going to end up being diverging overall. So I just want to kind of give myself a virtual ray just in case I need it. Second one was aim for the middle. Okay. These I can see don't interact, so we'll have to extend them backwards with virtual rays until they do. Okay, that looks fine. And then I guess if we really wanted to, just to show off, we can do this last one. So we'll go up. And then I think we wanted to come backwards. And that's why we don't do 3 rays, because they all kind of don't intersect at the same point. The best way to do this would be to use drafting software to get those angles absolutely right. Okay. So where's the image? It's certainly not over here on the real side. It's going to be back here. And which ones do we like the most? We can cook our books a little bit. Let's say they're about there. Yeah, why not? So our guesses are the image distance is 5, 6, 7, 8, 9, 10, 11, minus 11 because it's on this minus side. Its height is 2. And it's upright, so it's positive. And then it's clearly virtual and it's clearly upright. So virtual, upright. Okay, looks good. Now prove it. So I think P was 5 and F was plus 10. So 1 over 10 equals 1 over P, which was 5. It'd be nice if I had 10s here, so we'll rewrite as 1 over 10 equals 2 over 10. And then 1 minus 2 is -1, so -1 over 10 equals 1 over I. The image should have been at minus 10 centimeters. And the magnification should be minus I over P minus -10 over 5. And again, this shows the weaknesses in the picture. It's not great for getting quantitative numbers, but it is good for qualitative things. Virtual, upright, roughly where in the picture is it. These are to help you catch sign errors. Okay, so what do we know about this type of lens? It is apparently a magnifying glass. So the converging lens allows us to make magnified virtual upright images. So that's using it the way you're supposed to with the magnifying glass close to the surface. But if the object is really far away, now we're burning ants with the magnifying glass and with the sun being the faraway object, right? You're projecting real images that focus real rays and put an image, a condensed image of the sun on paper or, you know, whatever you're burning. Okay. So that's the converging lens. The other option, I guess, is a diverging one. We had a diverging mirror, which was just a convex mirror. And there's a little bit of an anti-symmetry here between lenses and mirrors, right? So concave mirrors were converging, but convex lenses were diverging. So this will be also an opposite. The diverging lens is standardly represented as double concave. It doesn't have to be this way, and we'll make some exotic examples later, but for the sake of demonstration, they're always labeled as biconcave. Okay, let's make this kind of big enough to where it'll fit inside. So what do we like? Let's use the same numbers we had the first time. P equals 15 centimeters. Here's one of the F's, is 10. And here's one of the F's, is 10. So use our mirror trick, right, to figure out which one's which. If this was the first surface and if this was a mirror, then the center of curvature would be on this side and the focus would be on this side. This is the true focus. This one, fake. So if we were doing our, if we were going to do our rays, we want to come in flat. And now we want to diverge through that focal point. And because it's divergent, I'm already writing myself a note. Use virtual rays, because I know I'm not going to have this work out. Okay, the other one is aim for the very center. That's kind of the easiest ray. So our ray would come through and continue to go through. And then technically there's a virtual ray on top of this, right, that goes backwards. So I'll dot it in just for our benefit. Okay, and the last one is go through the fake focal point. So we want to aim all the way over here to this ridiculous one on the right. And then once we hit that plane, remember we got to flatten out. And this is going to end up being a perfect picture. Looks really good. Okay. And just because of how good it is, I'm fairly confident in the numbers that we draw out of this. That might be wrong, but this will be our image. So what are our takeaways? The image looks like it's negative 5.6. It's like minus 6 centimeters. It is demagnified, right? Smaller, so this is 5 and this is only 2. So it looks like it's 0.4 or 2/5. That's the demagnification, and it's virtual and it's upright. Okay, and now to go through and prove it. This true focus is actually minus 10, right? Because it's here on the minus side, because the light goes through a lens and then it bounces back negative. Okay, so as we do this, I get 1 over F is minus 10 equals 1 over P over 15 plus 1 over I. Hopefully I don't have a kind of brain fart on arithmetic. What's common to these two is 30 again, so this looks like minus 3 over 30 equals, looks like 2 over 30 equals 1 over I. And minus 3 minus 2, that gives me minus 5 over 30. And maybe I am going to brain fart after all. 5, 10, 15, 20, 36. This was exactly 6 centimeters. And I had a suspicion this was a good picture when all 3 of these landed at the same point. Okay, magnification is minus I over P, of course, which is negative 6 over, we had 15. And that's 3, 6, 9, 12, 15, so 2 out of 5. Where these cancel. So it's virtual and it's upright. Upright because of that, virtual because of that. So that's a diverging lens, and out in the real world, not a lot of cases where you might use one. If you wanted to make images smaller, that's where you use diverging lens, and I say out in the real world, we don't see them very often. However, these are used to cure myopia or nearsightedness, which is a far more common condition than farsightedness. So the truth is, it's not obvious, but diverging lenses are a lot more common.